In this video, we'll find the angle between two planes in the vector equation and the parametric equations of the line of intersection between the two planes. Now let's talk about angles between planes first. We talked about this briefly in the other video. If two planes are parallel to each other, say we've got plane 1 like this, and plane 2 is like this. The normal vector of plane 2 and the normal vector of plane 1 are parallel to each other. Now it's possible that one of them could be pointing down, the other one could be pointing up, but they're still parallel to each other. So if the planes are parallel, the normals are parallel. So let's write that down. Just note to self. Plane 1 is parallel to plane 2. If and only if, the implication goes both ways. Or N1, is parallel to N2. And remember, two vectors are parallel if and only if N1 is equal to a constant times N2 for some constant C, some real number C. We also said that if the planes meet at a 90-degree angle, well, if that's the case, the normal vector to this plane, it's N2, and the normal vector to plane 1, N1, those have to be perpendicular to each other or orthogonal to each other. So plane 1 and plane 2 are perpendicular if and only if their normals are perpendicular or orthogonal. And remember how we can determine using vector operations whether two vectors are orthogonal. The only way they're orthogonal is if their dot product is 0. Now at the end of the last video, I showed you how to find the equation of the angle between the two planes, and I think I made it slightly more complicated than it had to be, so I want to do that again here. Let's say this is plane 1 and this is plane 2. It's meeting at some angle. And that angle is theta with plane 1. All right. Now, it's possible that one normal vector is, this normal vector to plane 1 is pointing just straight up, and the normal vector to plane 2 is at a different angle over here. It's pointing straight up from this plane. In that case, the angle between the two normal vectors is equal to that angle theta that's over here. Now, it might also be the case that instead of using this vector, this N2, to be the normal vector to N2, we choose to use the opposite one, the one that points the other way. I'm going to call that N2 with a star on it. Now the angle between the two normals is obtuse instead of acute. And I said, well, if the angle between the two normals is obtuse, do pi minus the answer that we would get using that formula. And then we said if the angle is acute, you can just use the angle that you get using the formula. Here's an easier way. We always want the smaller angle between the two planes. And that means we want to draw the normals so that they're roughly going in the same direction, so that we're talking about that smaller angle between the normal vectors. We want the angle between those two normals, not those two normals. So this is what we do. using the dot product formula, the geometric definition of dot product, we know the dot product of n1 and n2 is the length of n1 times the length of n2 times the cosine of the angle between them. Now, if I want the acute angle, it turns out all I have to do is take the absolute value of that dot product. And now we're going to solve for theta. So cosine of theta is the absolute value of the dot product of n1 and n2 divided by the length of n1 times the length of n2. So theta is going to be the acute angle between n1 and n2. So it's going to be this. The acute angle between the two planes is, oops, how did I miss the cosine? The arc cosine of this. So bad, I'm going to write it again. Theta is the arc cosine of the absolute value of n1 dotted with n2. That's a number. Take its absolute value, and we divide by the length of n1 and the length of n2. Because theta is the angle between the two planes, is the angle between n1 and n2 when they're headed in the same direction. If they happen to be headed in opposite directions, just multiply this one by -1, and then you're going to get this other vector over here. And then the angle between them will be acute, and then the angle between them will be given by, the angle between the two vectors will be equal to the smaller angle between the two planes, and that will be given by this formula. So I just wanted to do that again briefly. Okay, so that way you can just use the absolute value every time rather than having to subtract an angle from pi. All right. So now if I want to find the angle between these two planes, all I have to do is find the normal vectors. If they're not parallel to each other, they'll take their dot product. And if the dot product's not 0, I'll go ahead and finish this and substitute my two lengths and the dot product into this formula to find theta. So first, I'm going to call this one plane 1 and this one plane 2. Remember how we find the normals? You just read off the coefficients of x, y, and z. So we have a 6, a -3, and an implied 1. So this normal is 6, -3, 1. And here, we read off the coefficients of x, y, and z. We have -1, 1, and 5. And those are the components of that normal vector. Obviously, if I multiply this one by -6 to make that first component 6, I don't get that vector. So n1 is not a constant times n2, so the planes are not parallel to each other. Now let's compute the dot product and see if these planes meet at a 90-degree angle. So we'll do n1 dotted with n2. So I forgot a minus. Remember how this works. You multiply component by component and add. So we do 6 times -1 and add -3 times 1 and add 1 times 5 and add. So we have -6 minus 3 plus 5, so that's -9 plus 5, or -4. So the angle between n1 and n2 is obtuse because this is negative. So we're in this case. Like, I don't want to be in this case. I want to be in this case. So I could just multiply the second vector by a -1 to flip it, and then take the dot product, and then use this formula to find the angle between the two vectors. Or we could just take the absolute value of that dot product and put it over here. So we're just going to take the absolute value. Notice that the dot product's not 0. Since the dot product's not 0, that means the two planes are not perpendicular to each other. So now let's find the cosine, or the angle between the two planes. Theta is the inverse cosine or arc cosine of the absolute value of the dot product. It's going to give us the acute angle between the two planes, divided by the lengths of the two normal vectors. And we found the dot product already. It was -4. Now I need to find the length of n1. So take 6, -3, and 1, square them and add them and take the square root. So I've got 36 plus 9 plus 1, so 36 plus 10 is 46. So square root of 46 goes right there. And then the length of the second normal vector is -1 squared plus 1 squared plus 5 squared. Take the components, square them and add them and take the square root. 1 plus 1 plus 25 is 27. Okay, I'm going to use my calculator to evaluate that, and it gives us the angle between the two planes. So inverse cosine of 4 divided by open parentheses for the denominator, square root of 46, arrow out of the radical, times square root of 27, arrow out of the radical, close parentheses for the denominator, close parentheses for the inverse cosine, and hit equal. And it looks like the acute angle between the two planes is 83.5 degrees approximately. All right. So we've got a couple of planes. They look like this. They're nearly at a 90-degree angle, but this one's tilted just a little bit, so that the angle between them is 83 degrees, 83.5 degrees approximately. So now I want to think about this. Here's plane 1, and here's plane 2. And that's 83.5 degrees. It's hard to draw. I really respect people that have a talent for this. Okay, so that's 83.5 degrees. And we were asked to find the equation of this line. The line of intersection of the two planes. Now remember what we're looking for when we're looking for the equation of a line. We want parametric equations, so I need an x0, a y0, and a z0. And if the direction vector of the line is ABC, we're going to have AT, BT, and CT. So these are the parametric equations of the line. We've got one free variable, t, and as t increases, we're at different locations on the line. The question is, how can we find this? How can we find these three functions of t that will ensure that we lie on this line? Well, one way to do it is to simultaneously solve our system of equations. Now we've got two equations with three unknowns. I don't know if alarm bells went off in your head, but when I was a student, my alarm bells would go off and I'd say, hey, I can't solve a system of three equations, or two equations with three unknowns. I can solve a system of three equations with three unknowns, or two equations with two unknowns. But if the number of equations and the number of unknowns are not the same, they don't match, I'm not going to be able to find one solution. And you're absolutely right. We can't find one solution. We want infinitely many solutions. We want a whole bunch of solutions that all lie in the same line. So that's what we're looking for. So that means we're going to have one free variable. So what does that mean, a free variable? In this set of parametric equations, the free variable is t. I guess the easiest way to compare this, to describe this, is to look at the equation of a line from just algebra. Here I've got two variables, x and y. M and b are constants, they're known. But one of these variables is free. We call it the independent variable. I can choose x, and then once I choose x, I'm forced to make y equal to m times x plus b. This relationship has to hold for us to be on that line. But I am free to choose x. So there's one free variable there. When we're looking at a line in three-dimensional space instead of two-dimensional space, we also have one free variable. And in this set of parametric equations, the free variable is t. If you give me a t, then x and y and z are predetermined. Or actually, if I know z, if I know what z is, well then if I know what z is, I know what t is. And if I know what t is, then I can find x and y. So we're going to have one free variable here because it's one-dimensional. We're going to talk about having two free variables when something is two-dimensional later. And I'll let your linear algebra teachers teach you more about that. But there's a lot more beautiful math coming that relates to that. So all that is to say, I've got two equations with three unknowns, and that is totally fine. I want to solve both of these equations at the same time. And so initially what I want to do is I'd like to get like two of my variables in terms of a third, just like I was talking about over here. If I know what z is, then I know what t is, and if I know what t is, I can find x and y. So let's find x and y in terms of z. So let's say I'm solving this system of equations and I want to get rid of the x's. Just like we're in algebra class, I've got a 6x here and a negative x. I'd really like this to be a negative 6x so that when I add them together, the x's are gone. Now that can be done if I call this equation 1 and this equation 2, and I multiply equation 2 by 6 and add it to equation 1. So let's do that. 6 times this is going to give me a negative 6x. 6 times y is 6y. 6 times 5z is going to be 30z. That's going to give me 6 times 5, which is 30. Add those together, and we get 3y plus 31z. Oh, that's ugly. Equals 35. Man, that's an ugly one. That's okay. We're going to solve for y in terms of z. So we have 3y equals 35. I'm subtracting 31z from both sides. And then let's divide by both sides by 3. Oh my goodness, that's ugly. So I've got y in terms of z. All right. And that was because I got rid of the x's. Now rather than getting rid of the x's, this time let's get rid of the y's. So here was my original system of equations. I had 6x minus 3y plus z equals 5, and negative x plus y plus 5z equals 5. This is equation 1. That's equation 2. And this time, I got rid of the x's first. Now I'm going to try to get rid of the y's. I've got a negative 3y and a y. I'd like this to be a 3y so that those cancel, so I'm going to multiply equation 2 by 3 and then add them together. So I'll have equation 1 plus 3 times equation 2. Leave equation 1 alone. Multiply everything here by 3. Every single part. Don't forget the right-hand side. A lot of students forget the right-hand side. So I multiply this by 3 and I get negative 3x. Multiply that by 3, I get positive 3y. Multiply that by 3, I get 15z. And that equals 15. So I add these together. Oh dear, this is ugly, isn't it? That's okay. I get 3x plus 16z equals 20. And we can solve this for x in terms of z. So we subtract 16z from both sides. And we get 3x equals 20 minus 16z. And then we can, oh, somehow I missed that 3 dividing that 35 over there. Sorry, guys. This should all be 35 minus 31z divided by 3. Now let's take this and divide by 3. Okay, so that's my x value. So you might say x is going to be 20 minus 16z over 3. And y will be 35 minus 31z divided by 3. As long as z is just z. No matter what z is, this will hold up here. You say, well, Miss Townsend, that doesn't actually look like my parametric equations. My parametric equations have t's in them, not z's. You say, well, okay. Let's let z equal t. How about that? Then if z equals t, x equals 20 divided by 3 minus 16 over 3 times t. And y equals 35 over 3 minus 31 over 3 times t. So now we've got 3 parametric equations of the line. It looks like when x equals 20 over 3, this is when t equals 0, y equals 35 over 3, and z equals 0. So one point on this line comes from setting t equals to 0. So we get x of 0, y of 0, z of 0. And that's given by, it's given by 20 over 3, 35 over 3, and 0. All right, so those are the parametric equations of the line. Oh, guess we asked for the vector equation as well. And a vector equation of the line is given by r of t, and it has components x of t, y of t, and z of t. And x of t is that 20 over 3 minus 16 over 3 times t. Y of t is 35 over 3 minus 31 over 3 times t, and z is just t. Now, people are going to get different answers. If you wanted, you could choose z to be 3t, and if z was 3t, then this wouldn't have to be 31 over 3 times t, it would just be 31t. I mean, you could change everything by multiplying all the t's by 3. There are a lot of different things you can do. This is just one of many possible answers, but it's got an x of t, a y of t, and a z of t. And that describes where the original planes, this plane and this plane, meet.